going to draw the Earth here. Here's the Earth, right, and it's rotating on its axis. So there's its axis, and it's rotating, right? And so one time around is one full day. And it takes 24 hours to do that, which is 86,400 seconds. So that's the time. To get the average angular velocity, you also need the angular displacement. How many radians does the Earth go through in one day? How many radians? 2 pi radian, right? So the average angular velocity, which is angular displacement over time, is 2 pi radian over 86,400 seconds. So that is 7.27? Yeah. 7.27 times 10 to the negative fifth radians per second. Okay, so that's what we're looking at for the angular velocity of Earth. So now let's look at what we're looking at here. I'm going to take the Earth, I'm going to rotate it 90 degrees. So if I do that, we will be looking down on the North Pole, right? So I just took this and I rotated it. So now we're looking down at the North Pole.
I had it right.
So there's someone standing here on the equator, and the Earth is rotating this way. Right, so their linear speed or their tangential speed, right, you know they're going in a circle. So tangent to the circle goes like that. So like let's say the Earth stopped rotating and the instant they got here. And if there was no gravity, they would fly off into space, right, at some speed v. That's their tangential speed or the linear speed. So to get that, all we got to do is multiply by the radius. So v equals r omega. So here's the radius of the Earth. And they're moving with the angular velocity of the Earth. So it's 6.38 10 to the 6 times the answer from here. Remember, radians isn't a unit. So you got meters here, radians per second here. So it's just 464 meters per second. So if we go back up to this here, right, the person on the equator, who's standing here, is moving at 464 meters per second. But we are about halfway between the equator and the North Pole. So maybe we're about here. So who is moving faster, linear speeds faster, us or somebody at the equator? Not the same. The equator, right, because they have a bigger radius. The bigger your radius, the bigger your linear speed. We all have the same angular speed. Right? We're all going around the axis. Let's see, we're doing this. They're doing this. We're all going around the same axis. So we have the same angular speed, but because their radius, this is a big R, this is a smaller r, right? So their v is going to be bigger. So they're actually moving faster. Somebody at the North Pole, if they were exactly at the North Pole, what's their linear speed? 0. Right? They're just rotating like that. You're looking at the weed whacker. Okay, and what we have is a cord, right? It's 0.21 meters. And so it's spinning really fast, right? The weed whacker spins really fast. So it's tracing out this shape, right? That's not really a good circle. Let me start with a circle. Right, so we got our circle. We got our 0.21 meter radius, and the weed whacker is spinning really fast. It's just spinning, 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 spinning. Okay, and it's spinning at 650 radians per second. So if we wanted to know, and this, it doesn't ask this, but how many revolutions is that? So 650 radians every second means that 2 pi radians is 1 revolution, right? So that means it's actually 103.5 revolutions every second. So it's moving really fast, okay? So what the question's asking now, part A wants to know is how much time is needed to go 0.61 radians. So let's draw 1 radian on here. So 1 radian would be when this is 0.21, right? Then we have a radian. But it's not asking for that, it's only asking for 0.61 radians. So that would be something like that, right? Not a little more than half. So this here is 0.61 radians. This shaded area here. So it wants to know how long does it take to do that if it's moving at 650 radians every second. So let's list out the variables here. So omega is 650 radians every second. And we know that we're interested in a displacement of 0.61 radians. How much time? So we have an equation for that right here. So omega is delta theta over time. So 650 equals 0.61 over t. So it's a very small number, 9.3 times 10 to the minus 4 seconds. Right, to do that. Now the second part of the question is asking, in that time, as it goes that distance, what linear distance, right? Or basically the arc length here. So what distance does the tip go along the arc length in a time, or in a time equal to that, or in a displacement equal to that? So we know that d equals r theta, right? That's just this equation rearranged. I have it written here. So you could get your linear quantity by multiplying by the angular quantity. So it's 0.21 times 0.61, or 0.13 meters. So d here is 0.13 meters. The best way to approach this is list your variables. So you know omega I is negative 110. Omega F is negative 330. Time is 14 seconds. And so then alpha is the change in angular velocity with time. It should all be very simple for you guys. It's kind of review. So you got negative 15.7 radians per second squared. Okay? We got the same list of variables here. We're finishing at 83.8 radians per second in a time of 1.5 seconds, 1.75 seconds. We want to know the initial angular speed, and the key here is making your acceleration negative, right? Because the fan is rotating in a counterclockwise direction because the final was positive, and we know was slowing down, so the initial had to be positive as well. That means the angular acceleration had to be negative. So then you're just going to put them in your equation here. And what was it? It was 157 radians per second squared.